This is a short instructional video for the Acoustylyzer, the portable FFT analyzer. It's about a $1,000 device that allows us to interpret turbo expander vibration signals. The signal comes to the analyzer through a BNC connection. Here it is shown connected to our vibration test system, but typically it would be plugged in as shown in this picture to the Bentley Nevada system, or the BNC connection on a Bentley Nevada 990 vibration transmitter, or into the front of the Allen Bradley Dynamics 1444 module, depending on the system. The other side of the cable is an RCA plug, which is plugged into the top side of the analyzer. From the initial menu, you can choose from different options whether you're monitoring vibration, noise, or doing a calibration. In this case, we're choosing FFT. Use the up and down arrows and then hit the center button to select it. Navigate with the buttons 1 click down and 2 clicks to the right. You can see reverse video that tells you which part of the screen is active. When you highlight this section and hit enter, you get control over the location of the cursor on the FFT plot. Push the right button or the left button to move the cursor. As we push the right button, you can see the cursor moving to the right on the screen. Note that the frequency displayed at the top is showing in Hertz. You need to multiply by 60 to get RPM. By comparing to the odd-ray system, you can see that the primary synchronous spike is around 25,000 RPM. This is about the same as the 400 Hz shown on the Acoustylyzer. Now we push the right button to move the cursor further to the right. Remember, you can only move the cursor when the cursor box is flashing. Now the cursor is on the other peak, which is 800 Hz. This is 2 times the running speed. Moving to the left with the left cursor button, we move all the way to the 60 Hz point. This is the line frequency and is not related to the vibration of the shaft at all, but can be the cause of high indicated vibration. Now hit enter on the analyzer and you'll see that the cursor box stops blinking. It is still selected, but it is not active. We move the selection box 1 click to the right to select the vertical scale. The value is 120 decibels, which is the amplification for the magnitude of the signal. The 120 is just a reference number. We hit enter on that to make that input active, and we use the up and down buttons to set the vertical scale. Going up, as we increase to 150 dB, the signal is completely off scale and disappears. Using the down arrow, the reference signal is decreased back down to 80 dB. Then the noise at the bottom of the screen dominates the signal. You can see that the noise in the odd-ray system is also visible as grass at the bottom of the screen. Setting the vertical back to 120 cleans up the signal so that it's readable. Push the enter button so that we're no longer active on the vertical scale. Now use the down button to highlight the range at the bottom center, where it says 1.08 kHz. That is the total range from the start to the finish of the scale, the full scale range. Push enter to make that button active. Now we move with the up and down buttons to change the range. 8 kHz for the whole scale is too much, so we reduce it back down. 1 kHz is a good number for the machine that is spinning at 30,000 RPM. It allows you to capture all the way up to 65,000 RPM, which is 2 times running speed. The up and down arrow changes the overall range, and the left and right arrows adjust where the 0 point is on the scale. We'll set it to 1 kHz range, and then we'll set the left side all the way down to nearly 0. This way we're sure to catch the 60 Hz in case there's a line frequency noise. We'll hit enter to accept the range. You can see that we have a similar range on the odd ray, trying to capture the synchronous peak, the 60 Hz peak, and also the 2 times synchronous peak. It's good practice to be sure that your signal is live by adjusting the vertical axis. Use the buttons to select the vertical axis range and hit enter. If you are zoomed in to a higher scale like 120, the signals don't change very much. When you set that level down at a low number, like 85, you can see the noise at the bottom fluctuating so that you can be sure that you have a live signal. We'll hit enter to finish adjusting the vertical scale. Now while we're zoomed in, let's see how you pause the signal. Use the left arrow to go to the pause button and hit enter on the pause button. This freezes the signal. While it is paused, you can still adjust the scale to zoom in or out. Another way to check to be sure you have live data is to simply pull the cable and be sure that the signal goes to 0. You will not trip the machine when you do this. The final step is to be able to store this data. We move with the arrow keys up to the very top of the screen to the button that says MEM for memory. Hit enter on that button. There are two options for storing data: store plus bitmap, which gives the data and an image, or just store. To store the data, put the cursor on store plus bitmap and hit enter. To view the data, we go back to the memory screen and highlight View Delete, and you will see the data that you have stored so far. This is the last set that we stored. If you hit enter, you can see the last plot. You can also delete files from this screen. The escape button will bring you back to the exit button. Hit enter on the exit button to go back to the FFT. I want to give a little more explanation on the different frequencies we expect to see. So I've shown this earlier on the moving picture, but this is the synchronous vibration. When you do it right, the synchronous is right about in the middle of the screen. You want to make sure you've got enough range to cover the supersynchronous, the 2 times harmonic off to the right, which becomes a very large peak if you have vibration band elimination. And then subsynchronous noise is on the left side of the main peak. This handy-dandy chart will help you understand the results of the FFT measurement. This information is also on the Atlas Copco Gap wiki. This page is for subsynchronous vibration, and depending on what sort of peaks and valleys you're getting, you can understand what the source is, whether it's acoustical noise, whether it's a bearing problem, oil whirl, oil whip. All of these can be sort of determined by what you're seeing on the FFT analysis. Sometimes a single FFT snapshot tells most of the story, but often you need to watch the FFT real time as the speed or the other process parameters change. For example, a shaft critical speed or a structural resonance doesn't really shift the frequency when the machine speed is changing, so that makes it easy to identify them. But oil whirl that occurs at about 50% speed always tracks with speed. So then you can look at also the oil temperature changes. Oil whirl is usually worse with cold oil. If you have a subsynchronous that's around 70% of speed and tracking with speed, that's often high pressure gas in the wheel seal and around the wheel shroud. It's called wheel cross coupling or seal cross coupling. It does track with speed. It's not very sensitive to oil changes. It will be a little bit better with cold oil, but it is often sensitive to changes in inlet guide beam position. So you may need to change inlet guide beam position while you're watching the FFT real time to see if it's a wheel cross coupling problem. This page explains how to interpret synchronous vibration. Synchronous means there's a peak at running speed. It's the most common situation because unbalance causes a once per turn force. So if you have synchronous vibration, you're going to need to look at the other symptoms. You can change the speed while you're watching the FFT. So if the vibration increases with the speed squared, then it's probably in balance. What I mean by that is if you double the speed, the vibration goes up by a factor of 4. So you have to do the math, but it's an easy way to see if it's unbalanced. If the 1 times or the synchronous peak increases without any kind of a speed change, then you might have a Morton effect in your hands, which is a thermal bowing of the shaft. This page describes the supersynchronous and electrical noise. The most common supersynchronous for our turbo expanders is a vibration band delamination, and that shows up as multiple harmonics. You'll see a 2x peak and a 3x peak and a 4x peak. You'll see many harmonics, all of which are about the same as the 1 times peak. And none of them are an indication of real vibration. It's just a measurement error because of the vibration band problem. The other thing that's common for a non-synchronous measurement is electrical noise, which happens at 60 hertz if you're in North America, 50 hertz many other places in the world. It's often a problem that the customer says, I've got high vibration, and when you pull up the FFT, you find out that it's mostly 60 hertz or 50 hertz. It's a very good thing to be able to check out with the FFT. Now, if you have an expander generator with a coupling, you might see a strong 2 times, which is a misalignment problem. One last thing, before you get to the plant, it's a good idea to check out your cables and the analyzer, make sure that you know how to use it and everything's working. The simple way to do this is to take the test tones, which are available on our network, and download those test tones either to your iPod or your laptop, cell phone, whatever, something that can play them. This is going to allow you to create a sound file that's going to be read by the AL1 unit and test and see if it is reading what it should be reading. Each of those test tones is labeled with the frequency that it's running at, so there will be a single peak at that frequency, and you can check and make sure your whole system is working. There's an additional little cable piece that's shown here that you have to use to connect between your sound source and the BNC connection. It's very simple. It's a good idea to do, though, before you get to the plant.
Anything else, Mike?
Nope. It's a good day here in California.